Hello everyone, welcome to the online lecture series of the course EE204 Digital Electronics and Logic Design, Module 4 Sequential Circuits and Asynchronous Counters. Today we'll be studying about a modulo n counter or a mod n counter. We have already seen that the number of states through which the counter passes before returning to the starting state is called the modulus of the counter. Sometimes a counter may have a shortened modulus. That is, this type of counter does not utilize all the possible states. Some of the states are unutilized or invalid. We have already seen that for a counter with n bits or n flip-flops, it will be able to count up to a maximum of 2 raised to n unique states. So a mod n counter basically will be counting states which may be less than or equal to the maximum count. So designing of a mod n counter, you have to select the number of flip-flops according to the number of states you have to count. The number of flip-flops required to construct a mod n counter equals the smallest n for which n less than or equal to 2 raised to n. A mod n counter divides the input frequency by n and hence it is called a divide by n counter. A counter which goes through all the possible states before restarting is called a full modulus counter. A counter in which the maximum number of states can be changed is called the variable modulo counter. The final state of the counter sequence is called the terminal count. Now let us take an example for a modulo n counter. So we are going to design a counter which is having 10 states. Since the counter is having 10 states, it is also called as a decade counter or mod 10 counter. The counting sequence is from 0000 to 1001. Since this sequence starting from 0000 to 1001 represents the equivalent binary of the decimal numbers from 0 to 9 respectively, and hence the decade counter or a mod 10 counter is also called as a BCD counter. So there are different names for this counter: decade counter, mod 10 counter, or a BCD counter. Observing the circuit diagram, it is clear that the first flip-flop is provided with the original clock signal and hence its output Q0 will act as the LSB, and the farthest flip-flop from the flip-flop provided with clock, that is the last flip-flop, and its output Q3 will act as the MSB. Here, along with the flip-flop circuits, you have to use some logic circuit using gates to restrict the count to the required value. So design is very simple. Terminal count of the counter is 1001, and for the 4-bit ripple counter, the next count value is 1010. So this 1010 state we have to reset to 0000. That is the initial state of the counter, and we have to continue the operation. So logic we are going to make is we have to use some circuit so that the state 1010 get resetted to 0000. So all you have to do is that use all the ones in that next state, that is 1010, and make a logic such that it will clear the flip-flop. So here the bits or the output from Q1 and Q3 will be 1. So I am using those two lines as the input for a NAND gate which will provide a 0 only for Q1 and Q3 equal to 1. This case will be never occurring in the any of the 10 counting states. From 0000 to 1001, you will never have a counting state in which both Q1 and Q3 are 1. The point to be noted is that the logic which you are going to clear the flip-flop to its initial starting case, it should not occur in any of the normal counting states. So I am using Q1 and Q3 to make a logic to clear the flip-flop, and that is connected to the all the asynchronous clear inputs of the flip-flop. So upon obtaining Q1 and Q3 both equal to 1, the NAND gate will provide a 0, and for all the other cases it will be providing a high value. Now let's have a simulation of the decade counter circuit. You can see a similar circuit diagram as shown in the previous slide. Now on application repetition of clock pulse, the counter changes its states one by one. Initially, all the flip-flops are in the reset state, so output is 0 0 0 0. Next clock pulse will change the flip-flop outputs to 0 0 0 1. Next clock pulse will give you 0 0 1 0, then 0 0 1 1, 0 1 0 0, 0 1 0 1, 0 1 1 0, 0 1 1 1, 1 0 0 0, 1 0 0 1. So all the 10 states as obtained right now from 0 to 9, that is 0 0 0 0 onwards 1 0 0 1. So in a usual 4-bit asynchronous up counter, the next state will be 1 0 1 0. Here that 1 0 1 0 will be used to reset the flip-flop to its initial state. So here instead of the next state 1 0 1 0, we will be obtaining the resetted initial state 0 0 0 0. So I am going to give the next clock pulse. So upon obtaining the next clock pulse, the counter resets to its initial state 0 0 0 0. So this is the working of a decade counter. Now let's have the analysis of the timing diagram. Since the flip-flop outputs are used for obtaining the clock for the second flip-flop onwards, since we have given the original clock signal to the first flip-flop, on obtaining the negative edge, which is marked by the arrow symbol in the diagram, on that negative edge, the first flip-flop changes its state from 0 to 1. All the other flip-flop are not obtaining any negative edge, so their output will remain same. At the end of the second clock pulse, again the first flip-flop will change its state from 1 to 0. Here you have to note that this 1 to 0 transition will give you a negative edge, which will in turn trigger the second flip-flop. So second flip-flop changes its output from 0 to 1, and during the third clock signal, the first flip-flop changes its output from 0 to 1, whereas all the other flip-flop will remain in their previous state. On the fourth clock pulse, the first flip-flop will change its state from 1 to 0, and thus the second flip-flop will obtain a negative edge and it will change its state from 1 to 0. Here the third flip-flop also will obtain a negative edge clock signal. So the third flip-flop also change its state from 0 to 1. There is no change in the output for the last flip-flop. So on the fifth clock pulse, first flip-flop again changes its state from 0 to 1. All the other remains the same value. Sixth clock pulse, first flip-flop changes its value from 1 to 0, and thus the second flip-flop changes its state from 0 to 1, and all the other remaining same. On the seventh flip-flop and on the seventh clock pulse, first flip-flop changes its state from 0 to 1, and all the other remains the same value. And on the eighth clock pulse, the first flip-flop will change its state from 1 to 0, which will in turn trigger the second flip-flop to change its state from 1 to 0, and this will again in turn trigger the third flip-flop to change its state from 1 to 0, and also the third flip-flop will trigger the fourth flip-flop to change its value from 0 to 1. So like that the pattern will be continuing. So here you have to note one important feature of the asynchronous flip-flop. Since we have given the clock signal to the first flip-flop, it will change its state for every clock pulse. Since the second flip-flop is receiving clock signal as the output of first flip-flop, it will change its states for every 2 clock pulse. Similarly, since the third flip-flop is obtaining clock signal from the output of second flip-flop, it will change its state for every 4 clock signals. And the last one in this case, the fourth flip-flop change its state for every 8 clock signals. All these relationships are based on the primary clock we have given to the first flip-flop. So first flip-flop should change for every clock signal, second flip-flop will change for every 2 clock signal, third flip-flop will change for every 4 clock signal, and fourth flip-flop will change for every 8 clock signal, and so on. In general, you can have a relation. If you are connected n number of flip-flops in asynchronous mode, each flip-flop will change its state for 2 raised to n minus 1 number of clock pulses obtained to the first flip-flop, where n is the position of the flip-flop starting from the flip-flop with the basic clock signal. So I hope you have cleared the basic idea or working of a decade counter.